Show that when gravity is uniform, the torque due to gravitational forces on an object equals the torque applied by the full weight of the object at its center of mass point. So effectively, this is going to wind up showing my original claim that the center of mass point really is the balance point for an object in uniform gravity. And in that sense, if the center of gravity represents the balance point, it's saying the center of gravity point is the same as the center of mass point. But again, I want to really emphasize that that is only true in uniform gravity. If gravity is not uniform, these 2 points are different because the center of gravity really, its definition is tied to how gravitational forces act on an object. If the object is sitting in a point in space, or maybe it's a really large object, so that the gravitational forces on it are not uniform, maybe gravity is acting more strongly on one end of it than the other, that's actually going to shift that center of gravity point away from where the center of mass is. The center of mass on an object is independent of whether there's even any gravity at all. So in that sense, if you imagine a spaceship, right, maybe like a space shuttle or something like that, here on Earth, you could say it definitely has a center of gravity, it definitely has a center of mass. Well, if it travels really far away from Earth, not even just in orbit of Earth, but really far away to where there's no gravity at all, you could say, well, it's still going to have the same center of mass. It maybe becomes debatable whether it even has a center of gravity at that point if there's no gravity acting on it, right? Or if it's somewhere where maybe due to different nearby large objects applying different sources of gravity, it's maybe non-uniform in its region. And so again, that would change where its center of gravity point is. So that's kind of the different concepts here behind center of gravity and center of mass. But like I said, I'd really want to establish that here on Earth, we don't necessarily need to get all too worried about the difference between the two, unless we really, I guess, like to be geeky about that, I suppose. Speaking of being geeky, let's look at the answer. And maybe you can appreciate the joke I made with that. Actually, let's stick on this window here. This is quite a bit of geeky math here, I think, is what I'm calling it. And I mean that in the most positive sense. But anyways, it says here, consider the sum of all the torques of the gravitational forces. Oh, my goodness. Well, let's see. Can we're talking about summing up torques, right? And that's what was in that Wikipedia definition. We're talking about, therefore, moment arms with weight forces. And this is kind of using that really formal advanced definition of torque. And then it gets manipulated a bit here. And yeah, that's where the math, I think, is going a little bit crazy. It looks like I just moved that m to a different spot there. And then it's taking that same expression and manipulating that one by maybe multiplying and dividing in 2 places in a way that doesn't change it by the total mass m. And that gives us this result here. But this definition, this actually kind of resembles, right? If you look at this, this looks a lot like the thing I still have on the board over here, except I used r here instead of x's, and that's okay. I mean, I kind of used x here because we'd originally used that when we defined center of mass in an earlier chapter, but you know, using r as a position vector, kind of because it came from like moment arms, I think, but then regarding them as position vectors and interpreting that as therefore the center of mass point, and then using r to symbolize that. There's nothing wrong with that. You can do that. You can use a different symbol. You know, in that sense, physics is a little bit flexible in terms of what symbols to use, even though we have certain meanings associated with them. But then what wound up settling out at the end of the day is that this is the overall weight of whatever object I was considering. And so the interpretation of this is that if I want to consider the total torque on a system due to all the possible gravitational forces, I can model that as taking the moment arm to a single gravitational force at the center of mass point. In other words, in uniform gravity, this picture here showing that this is where I said as a single force equivalent, the force of gravity acts, that would also be what this formula for the center of mass gives us.